Mathematica notebook file. Mathematica has tons of these cool little animation things, and you can just download the free player to use them. You don't have to like own Mathematica or anything. So if you want to check out the stuff that they have, you just Google Mathematica player, and you can download it. So this is a little demonstration. I'm sorry, I don't think I can make it bigger. No. Oh, I can. Okay, so this is the area under a curve 1 over x to the n, and I've got the area from 0 to 1 shaded in blue, and then 1 to infinity shaded in pink. So this is the activity that you were working on last class, trying to conclude what these areas are. So for n equals 5, the integral from 0 to 1, so the area shaded in blue here, turns out to be 2, and the area shaded in pink is infinite. So that integral diverges. And then as I make n bigger, actually, I want to make this a little smaller. So as I make n a little bit bigger, 0.55, 0.6, 0.65. So the area in blue is getting a little bit bigger, and the pink area is still infinite. And then I'm just going to step forward, step, 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 step. And here's n is 0.9, right? The area under my integral from 0 to 1 is 10, and the rest of my area diverges. And then 0.95, 1. At 1, they both diverge. Okay, the area under 0 to 1 is infinite, and 1 to infinity is infinite. At 1, they both diverge, and then as soon as we pass 1, we switch. The integral from 0 to 1 is now infinite, and from 1 to infinity is now finite. So it has to do with how quickly the graph approaches its asymptote, right? So when n is less than 1, it approaches its vertical asymptote quickly enough that this area is finite. And then when you're bigger than 1, it actually approaches its horizontal asymptote more quickly. And now we get that this area to the right of 1 becomes finite. Finite meaning not infinite, yeah, meaning some amount of area that can be measured and given a number. Okay, so these are some useful integrals for comparison. The first two are things that you discovered last class and we just confirmed using Mathematica. If you take the integral from any positive number to infinity of 1 over x to the p, if p is bigger than 1, it converges, less than or equal to 1, diverges. And if you look at that same function, but integrate from 0 to any positive number, right, we looked at 1, but it's true for any positive number, of 1 over x to the p dx. If p is less than 1, it converges, and bigger than or equal to 1, it diverges. And then the integral of from any number to infinity of 1 over e to the ax, it converges for a positive and diverges for a negative. All right, so today we're going to look at trying to determine whether an integral converges or diverges, even if we can't actually do the integration piece, the antiderivative piece. Okay, so sometimes, even if you can't actually find an antiderivative and evaluate it, it's helpful to know whether or not you have infinite area or finite area. Okay, so we're going to look at being able to determine that even when the calculation of finding the antiderivative is ridiculously hard. All right, so suppose you know that the area from a to infinity under g of x is finite. Okay, converges. So you have a finite amount of area under this pink curve. So let's see, I'll do this in pink, from say 1 to infinity. So I'm shading the area under this curve. And I know that that is a finite area. right? Less than infinity, which means it's just some amount, like 100. I can assign a number to it. Okay. What can I conclude in particular about the area under f of x in that picture? Yeah, the area under f is less than the area under g, right? Because f is below g. So there's going to be less area under f than there is under g. And you know that the area under g is finite. So is the area under f infinite or finite? It's got to be finite, right? You can't be less than a number and be infinite. So the area under f has to also be finite. Okay. Right. So this is what we discussed last class. Um, it's a difficult concept to wrap your head around, right? So the example that I like to use, so you're adding up an infinite amount of stuff, right? How could you possibly end up with a finite amount, right? So think of this as adding rectangles, right? When you find the area under a curve, you're adding a bunch of rectangles. So we're adding an infinite number of rectangles forever. How am I going to get a finite amount? All right, so Sephora, I'm going to pay you an infinite amount of money. I'm going to give you some money every day from now until forever. Forever and ever and ever. I'm going to give you money. Are you going to be rich? It depends, yeah. So if today I give you $1, tomorrow I'll give you 50 cents. And the day after that, I'll give you a quarter. And the day after that, I'll give you 12.5 cents. And the day after that, I'm going to give you 6.25 cents, right? So every day, I'm going to take the amount I gave you the previous day and cut it in half and give it to you. Okay. And I'm going to do that forever and ever and ever and ever. So I'm always going to be giving you money, right? Every day. Are you going to get rich? No. In fact, how much am I going to give you? If I could do this forever. Yeah, almost nothing. It turns out I'm going to give you $2. Even if I could do it forever and ever until infinity, $2, right? So that's how you can add up an infinite amount of stuff and get a finite amount. So that's what's happening here. The reason that that works is because the stuff that I'm adding up is going to zero very fast, right? I'm taking the dollar amount that I'm giving and having it, so it's going to zero very quickly, which is similar to what happens to this function g of x, 1 over x squared, right? It goes to zero very quickly. So it turns out that the amounts that I'm adding are becoming so small that they never push the value past a certain limit. Is that clear? Okay. So if we know, right, if we accept, right, that this area under G is finite, that it only adds up to some finite amount. We actually did this calculation yesterday. What did it come out to? 2, I think. Well, let's see. We can use the little Mathematica player to do it. See if I make n 2. Oh, it doesn't go that far. Darn. Oh well. We did it yesterday, but I can't remember what it came out to. But it came out to some number, right? Instead of integrating from 1 to infinity, we went from 1 to b, and then took the limit as b goes to infinity. Okay, so we're assuming we know that that area shaded under G is finite. The area under F is smaller than the area under G. There is less area under F than there is under G. So that means I can conclude that the integral from a to infinity of f of x dx is less than the integral from a to infinity of g of x dx, which I know is less than infinity, less than, which is finite. So I can conclude the integral from a to infinity of f of x dx also converges. Okay, so now I'm going to kind of reverse things a little bit. I'm going to start by looking at the area under F. This like blue area there. Let's suppose, ignore the formulas because we know that that converges, but let's suppose that we know that that blue area under F is infinite. There is an infinite amount of area that I shaded in blue there. So I'm going to write diverges. Suppose you know that that integral diverges. What can you conclude about the pink area? It has to also diverge. If this shaded blue area is infinite, the pink area is larger than the blue area, right? It's always above. So if what you have in blue is infinite, then the pink also has to be infinite. Okay, so that means I can conclude that the integral from a to infinity of g of x dx also diverges. So this is called the comparison test. You can take the integral you're interested in and you want to compare it to another integral that you know converges or diverges, right? So if you can show an integral converges and then you find a larger convergent, oh, okay. You can show an integral converges if you can find a larger integral that converges, right? And you can show that an integral diverges if you can find a smaller divergent integral. So in practice, what we do is you try to find a simpler function, something that you know converges or diverges, right? A simpler function than the one in question, but with similar end behavior. And then we look to try to compare them. All right, so for example, I want to look at the integral from 1 to infinity of 1 over e to the x plus 1. Finding an antiderivative for this could be a pain, right? A u substitution won't work because the derivative of e to the x plus 1 is e to the x, and there isn't an e to the x in there. So, but I can still determine the convergence or divergence of this function without having to calculate an antiderivative. So let's compare what is a function that's similar to this integrand whose convergence or divergence we know. You look on the first page, I know that the integral from any number to infinity of 1 over e to the ax dx converges, as long as a is positive. Okay, so 1 over e to the x will converge. 1 over e to the x converges. So I want to compare what kind of inequality symbol should go between those two. The left is less than the right. Can you explain how you know that? Yeah, so that we have a plus 1 in the denominator, right? That makes the denominator bigger, which makes the whole fraction value smaller, right? When you make the denominator bigger, the fraction is smaller. So this guy on the left is actually less than this guy on the right. I tend to write less than or equal to's, even it's still true, right? Because it's less than or equal to. So I don't know why I do. It's just habit, I guess. So less than or equal to. And then if I integrate everything on here, integrate from 1 to infinity dx, integrate this from 1 to infinity dx, I know that this guy, the integral from 1 to infinity of e to the x dx, is finite, right? It's strictly less than infinity, some finite thing. So if you know that this integral is smaller than something finite, you know it also converges. So the integral I'm interested in here converges because it is smaller than a different integral that I know also converges. If you have a function that you know is convergent, our function is smaller than it, so it has to also be convergent. Yeah, so you want to look for, you want to like take this thing in the integrand and think about a function that has similar behavior, that looks similar to it, but whose behavior you know. Convergent or divergent behavior you know. Good question. If it turned out, if I wrote this down, if it turned out that I did, okay, so this is going to look weird because I know it's not true, but let's just say that that's the case, right? I know that this one is finite, right? When I integrate that from 1 to infinity, I know that that's finite. So if I have another function that is bigger than something finite, can you conclude anything about its finiteness or infiniteness? Knowing that it's bigger than something finite, does that let you know whether this is infinite or finite? No, why not, Ashley? It could be either still, right? You can always get another number that's bigger, right? Just because I know that this is a finite number, right? Like let's say I know that this is 10, right? This guy could either be 12 or it could be infinite. Either one is bigger. So if you have something convergent, if your function is bigger than it, you don't get to conclude anything. So the only way you get to conclude something is if you have a function that's convergent and you're smaller than it, or if you have a function that's divergent and you're bigger than it. Okay. So here we can conclude nothing. Just in case someone is reading this later. All right, let's look at another one. This time I want to look at the integral from 1 to infinity of x squared over x to the fourth plus 4x plus 1. All right, so I'm going to start by writing down this function. Actually, where to start? Okay, so I need something to compare this to, right? Doing the actual integration step here, finding an antiderivative, is going to be a real pain, right? I probably would have to, I don't even know, maybe complete the square in the denominator and then use the table. So if I want to know whether this converges or diverges, I have to compare it to an integral whose behavior I know. What function do you think we should compare to? 1 over x squared, yeah. I mean, I only have two choices, right? There are only two functions right now whose convergence or divergence I know. 1 over x to the p and 1 over e to the ax. So it's got to be 1 over x to the p. And why did you choose p to be 2 here? 1 over x squared. Yeah, yeah. X squared over x to the fourth simplifies to 1 over x squared. So if I can somehow compare these two, this function to 1 over x squared, I know 1 over x squared converges. So let's look at, okay, so if I just drop the, oops, that's next to the fourth, sorry. If I just drop the plus 4x plus 1 in the denominator, what's going to happen? This would become x squared over x to the fourth. What kind of symbol should I put in between there? How would they be related to each other? I would like it to be a less than. Is it a less than? We know the x's are always positive, right? So 4x plus 1 is going to be a positive number. And the x's are always positive because the bounds of integration are going from 1 to infinity, right? So if I have this 4x plus 1 in the denominator, I'm making the denominator bigger than just a plain old x to the fourth. So this 4x plus 1 makes my denominator a little bit bigger, which makes the value of the fraction a little bit smaller. So this fraction is smaller than that fraction. And then that it would be less than or equal to 1 over x squared. I know it's weird to write a less than or equal to, but it is true, right? It's less than or equal to, because they are equal. I just like to write a chain of inequalities. All right, now the 1 over x squared I know converges, right? So I now know that my function is smaller than a convergent function, so it has to also converge. So for me, it's helpful, instead of using the words convergent and divergent when I'm doing these problems, I use the words infinite and finite, or switch it, finite and infinite. Convergent, finite area, divergent, infinite area. And I think that really can help you think about what you're doing here. So I know the area under this curve is finite. The area under this curve is less than a finite number. It has to also be convergent. So even though we don't know exactly how much area there is, at least we know it's finite. Is this okay? All right, we'll do one more together. Integral from 2 to infinity of 1 over the cube root of x squared minus 1. So I have to compare this to a function whose behavior I know, that I know if it converges or diverges. I only have a couple of choices, 1 over x to the p or 1 over e to the ax. What function do you want to compare this to? One over x squared? Close. The cube root of x squared, yeah. Or x to the 2/3, yeah. I want to compare this to 1 over x to the 2/3. Right, so that's my leading term in the denominator. It's an x squared cube rooted, which is an x to the 2/3. So it's a similar approach to what I did in the last one, right? I'm looking at the biggest power of x. Now I need to compare these two. Take a couple minutes and see if you can try to put an inequality, a less than or a greater than or an equal sign. Relate those two functions to each other. Let's think about the relationship here. On the right, I'm taking my x, which is a number between 2 and infinity, so it's a positive number, and I'm going to square it and then cube root it. Okay. That's in my denominator. And in the left, I'm going to take my number, I'm going to square it, subtract 1, and then cube root it. So which denominator is larger? The one on the right. Square and then cube root is going to be bigger than square, subtract 1, and then cube root. So this denominator on the right is bigger, which means that that is the smaller fraction. Bigger denominator, smaller fraction, so I have that is the case here. And what do you know about 1 over x to the 2/3? Convergent or divergent? Divergent. Yeah. This is divergent. Right.
Are you looking at the first page to determine that?
To determine whether or not it's divergent? Yes. I'm just using.
That for p greater than 1.
Yeah, but 2/3 is less than 1. Okay, so this guy diverges, which means it's infinite, right? And this guy is bigger than it, right? If you're bigger than something infinite, you have to also be infinite. Right? So this one has to be also infinite. So that means that this has to diverge. Now let's just look at what would have happened if these two had been related in a different way. Now I know it's not true, just bear with me for a second, but let's say I wrote this. If we thought that that were the relationship, right? And I know this guy diverges. Which means it's infinite. Okay, so if you are less, so now I know that this guy is infinite, the area under this curve is infinite, so the area under this curve is going to be less than that because this is a smaller function. Being less than infinity, can you conclude whether it's finite or infinite? Right, you can't think anything. There's nothing you can conclude. Because there are some infinities are larger than others, right? Like think about the counting numbers, right? 1, 2, 3, 4, 5. How many are there? Infinite, right? Now think about the even counting numbers. 2, 4, 6, 8. How many are there? Infinite. But there are more of the regular counting numbers than the even counting numbers. So you can have two infinities, one is smaller than the other. So just because you're less than something infinite means nothing, right? So here I could conclude nothing. Okay, just like being larger than something infinite, sorry, being larger than something finite means you can conclude nothing because you could still be something finite, just bigger, or you could be infinity. Being less than something infinite, you could still be infinite, or you could be finite. We don't know. Okay, so now these are different kinds of problems than you've ever done before. These are like little mini proofs. So really, you just have to get a lot of practice with them. So I'm going to let you get some now, and I will come around and help as needed.